talk about spawning new. We don't have a fork, we have a spawn, and the way it works is, first of all, all tasks have the same memory map. So in other operating systems you have different memory maps, and each task has a C task record. This is a task record. All the stuff is thrown together in there. When the task is swapped out, the registers are stored here. When it's not running, I should say. I don't have the same terminology as Linux. Each task can have one. Each task on Core 0 can have one window. There are no child windows in TempleOS. So what that means is you make a pop-up if you want. All applications run on Core 0, and they create slaves on the other cores. So the FS segment register points to the current task, and the current task is not indicated by a PID. It's indicated by a, if you look up here, 3FD7, that's the task record address. It's always 8 characters, 8 nibbles. Anyway, so the FS segment register points to the current task record, and as a matter of fact, if you want, let's go right to that task's input buffer. Crosstalk, and then I'm just going to cheat here a little bit. No, let's not do it. 0x, what do we have? 3FD75C28, 3FD75C28, comma, dir. Are you watching? Ready? 1, 2, 3, go. I just stuck characters into his input buffer. I can put characters into my own input buffer by saying auto. When you're compiling the kernel, you want to put the answers to the kernel question in with auto. It's like standard in. It's like feeding standard in. So it can get tricky when you have pop-ups. So, no, yes. So if you have a pop-up, let's do yes. We have a 1. Pop-up, no. We have a 0. Okay, so that's a child task. It can be modal or not a child task. It's either a child task or it's global. So we were going to talk about fork. We don't have fork. We have spawn. I should say. Okay, so U0 my task cdoc star doc, and this guy says spawn address my task doc. Okay, you have a dot out. You have standard in and standard out. In TempleOS, you have the document that you are putting, you have the document you are displaying, and you have the border document. If we go to the task record, well, anyway, so goodbye. Let's see what this does. Watch this. Pow. Unused var doc expecting comma. Oh, I left that over. Expecting comma. What is your malfunction again? A? Oh, doc put. What is that? Shit. I could swear it's doc put. It's not. What? Okay, hold on a second. C task. No. It's doc put. I know it's doc put. What are you talking about? Doc put. See, current document. It's okay, I wasn't paying attention. Oh, there we go. Okay. There, we got goodbye. So what happened here is it spawned a task, it immediately exited, and it didn't do anything. Now if we say doc print task. Okay, so he's passing his standard out is being passed as a parameter. Let's look at spawn. You should memorize this. The address of the code, the address of the function, a data item, the name, and then the target CPU. -1 is the, anyway, I don't remember. I think it's the current. Okay, so okay, now let's go Control B. Let's do a tiny sleep for 100. Okay, it's gonna make 1,000 tasks, and they're all gonna sleep, and then they're all gonna print, and the standard out has a lock. So we got. That did not take very long. Okay, so let's see. Pow. Okay. So they all. Now, if you want to do multiple cores, job, I and 7. Pow. That's actually 7 cores. Let's slow it down so that we can see what's going on. Let's put it on. Let's put 10, and let's do 10 seconds. Ready? Pow. Okay, so these do not have windows. Okay, on the wallpaper is all the cores. They were waiting. Okay, so if you now. There is a trick. As a matter of fact, what we did is bad, because you see this code, this is in the memory of the parent. We execute those, and we are not synchronous. And then we exit, and we free the code memory. So this code memory has been freed if we exit. So we need to wait for them to finish. Well, if you want to do it the African way, you can do it like that. Now it's only a problem if it gets reused. Or we can, how would we do this? I64I. You know what we do? Tell you what we do. Block I minus. You might ask, what does this do? Well, how about let's kick this up to 10. Okay. Oh, I did it for a long time. We got now we don't have preemption anymore. We used to have preemption, but I got rid of it because my users are stupid. They can't handle. Okay, so you know what we do here? Here we say while count yield. And it exited. Beautiful. Beautiful. Just for grins, what do you think will happen if we say %d count? It's not going to be pretty. There is no preemption, and therefore this code pretty much executes atomically. Now, except for multi-core. Well, multi-core means you might not think we have multi-core, but we do. For I equals 0, I less than 1, 1, 2, 3, 1, 2, 3. Okay, we are going to make the computer sweat. Okay, so let's do. Oh, that's not going to be any good. Well, no. Anyway, it's multi-core. Take my word for it. So each task has a symbol table. Task inherit, or if it's not found in the child, it searches the parent. So if you say who minus R, there are no symbols. But if we run this, if we hit F5, it's a new task. If we hit include, it's the same task. Now if we say who minus R, so all the compiler symbols go into the, it's kind of like the scope of an environment variable, except anyway. So we can say count. Now let's unassemble my task. Do you remember? I want to point out, you see this lock? That's for multi-core. It doesn't always work. It doesn't put the lock on correctly for some. If you do a fancy addressing, it's only, well, anyway. So there we go. So all tasks have the same memory map at all times. All memory is accessible at all times. So for example, if I say address count over here, And over here I say I64 star pointer equals 0x3f D77 D90 star pointer equals 1, 2, 3, 4, 5, 6. And if I go over here and I say count 1, 2, 3, 4, 5, 6. So it's super simple. Other operating systems have to worry about interprocess communication. Well, everything is wide open and we're all on the same map. So sometimes I call this single process multiple thread as opposed to multiprocessing. I think to imagine the entire operating system has one process and all the tasks are threads, except they all share the same memory. It's I don't even know why I have to explain it. It's the simplest case. All memory is no paging, and there is paging, but it's not really used. Anyway.